Hi, this is lesson 5, entropy. This is kind of a confusing lesson, so let's go through it. Make sure you try this early to try to understand it. Come to office hours. All right, so just a few reminders. Up top is information on SI and tutoring. Tutoring, you can go. There are plenty of times available. All right, this week, Zoom will be office hours. Homework number 2 and 3 are due this week. Next week, we have office hours. We have quiz 1. Quiz 1 I'll tell you more about in lesson 6's video. There's also a review on Friday of next week, the 24th, and that's because our test is the following Monday. Homework number 4 is on Blackboard. 5 and 6 will be on Sapling. Due every Monday, Wednesday, Friday. Okay, so let's do a little bit of review. Last time we looked at Hess's law. Hess's law tells us I can manipulate different equations to get delta H. So here's a problem where we want to figure out delta H for this equation, and we're given these two equations. So now the first thing we always do is we say, hey, how can I get N2? Well, it's only in equation 1, so I would use equation 1. O2, I could get either from equation 1 or 2. So that's not going to be helpful. And NO, that's only available in equation 2. So I could either go and use equation 1 to get N2 right, or equation 2 to get NO right, and that's what we do here, right? First, we want half N2, and we have 1 N2 here, so we take number 1 and we multiply it by half. That gives me half N2 plus O2 going to NO2, so I basically took everything divided by half. That meant my delta H was also halved. And then to get NO in the right spot, here it's a reactant, here it's a product, so I need to reverse it. So I reverse everything. That also reverses my delta H from negative to positive. I sum these up, I get this equation up here. Oops, sorry. Notice some things cancel out. Something over here, it's 1 O2, here it's half O2, so that gives me the half. And then I just sum up these delta H's, and there's my answer. All right, that was Hess's law. And Hess's law was using heat. Okay, so already we've talked in 215 about compounds and elements involved. That's stoichiometry. Then we talked heat involved. Now we're going to talk about another way to describe reactions. And that's whether this reaction is what we call spontaneous or not. This is in chapter 16. And so 16.1 talks about what it means to be spontaneous. Well, in everyday life, if I say someone's spontaneous, that means, hey, they're spontaneous. They're going to go on a whim across country, right? In reactions, when we say spontaneous, that means it just naturally occurs, right? Under a certain set of conditions. And a non-spontaneous is a process that won't occur naturally. Instead, we need to put energy into it. For instance, think about this. If I have ice cubes and they turn into, so they go from solid to liquid, okay? This is spontaneous at room temperature. If I had ice right here, it would melt. But it's not spontaneous in a freezer. Ice isn't going to melt if I put it in a freezer. So under one set of conditions, 25 degrees Celsius, it's spontaneous. At another set of conditions, it's not spontaneous. Here's another example. If, let's say, I had this, right? I had a gas cylinder where on one side there was some gas, on the other there was none. If all of a sudden I open it up, what are they going to do? They're going to fill both sides. That would be a spontaneous reaction. But for the opposite to happen, that'd be non-spontaneous. Again, if I've had something that's hot on one side and cold on the other, so this is hot, this is cold. If I put these together, what's going to happen? The heat's going to transfer until they get to the All right, so we have some rules for spontaneity. The first is that it depends on the conditions, temperature and pressure. We showed that already with ice melting. The second is that if I have a spontaneous reaction, such as solid going to liquid, we say this is spontaneous at room temperature. If I have the reverse reaction, going from liquid to solid, this is going to be non-spontaneous, right? So if I have room temperature, the temperature in my house right now and your house there, and I had liquid water, it's not going to freeze. That's going to be non-spontaneous. The third rule or idea we should know about spontaneity is that just because something's spontaneous does not mean it's fast. A diamond will spontaneously turn into graphite, what you have in a lead pencil. But this is going to take a long time, thousands, maybe millions of years, right? So it's spontaneous, but it's not fast. All right, so let's look at spontaneous reactions and what makes something spontaneous. All right, so spontaneous reactions are dependent on three things. The first is the change in enthalpy for that reaction, right? The delta H. The second is the temperature. And the third is something called delta S, or the change in entropy. Okay? So S stands for entropy. Let's talk a little bit more about it. We're going to start off simple, go a little more complex, and then go back to simple. Okay? All right, so entropy is the measure of disorder of a system. It's in units of joules per mole K. Joules being energy, and per mole K, so per mole and temperature. We can talk about delta S as the change in entropy of a system. So S final minus S initial. So look at this example. Okay? Over on the right-hand side, you can see a dorm room where there's clothes all over the place. There's a laundry basket. This is a place that has high S. It is very disordered. Over on the right, or on the, left, right, this is a room that's fairly clean, this with a red blanket. Notice it's clean, the shoes are lined up. So this one has low S, or it's more organized, so it has less disorder. All right, now, in physics, we can also define S as based on heat flow, right? So if I have a reversible reaction, so going from hot to cold, right? It's the heat flow associated with it, right? This is something by two scientists called Carnot and Clausius, right? And so they say delta S is the amount of heat associated with this reaction at a given temperature. We're not going to use this equation. Another example of disorder would be something like rolling dice. Let's say I roll dice, and dice have 1 through 6. They have 6 sides, 1 through 6. These are all the possibilities. Okay? So I can define this as the number of what we call microstates, right? The arrangement of all these possible rolls. Well, S is equal to some constant times ln of W. And the higher S is, that means there's more likelihood of disorder. You can see here, to try to get a 7, right, there are a bunch of different ways. But to get only 2 with it, there's only one way, to roll 1 on each one. Okay? Now, this is the key point. If I do ln of 1, I'm going to get 0. So if there's only one way to do anything, it has an entropy of 0. We'll go back to this at a later time. All right, but for what we're dealing with in this class, we have low S and high S. High S means a lot of disorder. Low S means low disorder. Okay? Now, if I go from low to high, right, what's going to happen? My delta S would be positive. Okay? My amount of disorder is increasing. If instead I go from high to low, so I clean this room up, my delta S would be negative. All right, so let's go and let's talk about some chemical reactions. Okay, so S is higher when a system is in disorder. So if I look at these three cases, a solid, a liquid, and a gas, okay, the solid, everything's very organized. The liquid, it becomes a little more disorganized. And then for the gas, those gas particles are moving all over the place. So this has a high level of disorder. So S, entropy for gas, is greater than for liquid, and it's greater than for solid. And so if I go from a solid to a liquid, or solid to a liquid to a gas, my delta S is increasing. If I go the opposite way, that means that my S is decreasing. So my delta S is less than 0, going from gas towards a solid. Now, if my S will also increase with temperature. So as I increase temperature, those gas molecules or whatever, they're moving around more, and so it increases. Right? And so here is a plot of S, entropy, versus temperature. So if I have a solid, if I heat it up, S increases. Right? Once it gets to a liquid, it jumps a lot, but then it increases more. And then it gets even more, and it increases more. One example of gas, or of a liquid, think of a water pot, right? So I have that water, I'm looking down on it. At room temperature, nothing much happening. But I turn up that temperature, and what happens? It starts to boil, and I see a lot of action. That's entropy. Okay, so now there are other things that cause S to increase. One is the size of a system. So the bigger the molecule, or the bigger the system, whatever I'm looking at, the more entropy there is. Think about it. If you only had 3 people in a room, it's fairly organized. But now if you have 300 people in a stadium, they're all moving around, etc., and it's more disorganized. In addition, S increases for mixtures. So look over here at NaCl and water. So I have some sodium, that's the positive. I have some chlorine, my negative, and I have my water here. All of these make it very disorganized. So let's go through some examples. We can actually predict delta S based for different reactions. All right. Okay, so we're back at the board. I messed up, so I'm just going to redo this. You won't even notice, but I wanted you to know. I don't know why. So water freezing. What's water freezing? I'm going from liquid to solid. So in liquid, I have a whole bunch of water molecules and they're moving around. Once it's solid, now these water molecules, they aren't moving around as much. We have ice, right? So what's happening to my S, right? Well, this is more disorganized. So this will have a higher S than over here. So I'm going from high S to low S. I'm getting more organized. So my delta S is going to be low minus high. So, let's say this is 2 and this is 5. This will get me a negative delta S. Negative means it is becoming more organized. Let's do one other example. Let's say we're going from NH3 solid. We call this one negative. let's say we're going from NH3 solid to NH3 liquid. In this case, we're going from something where it's very organized to something where it's more disorganized. So this will be low S, this will be higher S. So now my delta S is high S minus low S. And so this is going to be a positive value, right? So this is bigger than this. This will be 100. This will be 50, whatever. So this is positive. Okay? Notice how going from liquid to solid is negative. The opposite way is going to be positive. All right, so we're going to do, so this is just an example, or these are our results. You're going to do 3 other examples, and then we'll talk about them in that video solution, right? This is video problem 5A. All right, once you're done with that, log that over, figure it out, make sure you're understanding all these cases. There's one other I want to do as a class, and that is this problem. Let's say we have PCl5 going to PCl3 plus Cl2 gas. So I'm going from 1 mole of a gas to 2 moles of gas, right? There's 1 here, there's 2 here. So notice, if this is my PCl5, and it's breaking apart to PCl3, and this is Cl2, right? Which one is more disorganized? Well, this one is, right? The reason being is that this has just more moles gas. So my delta S would be positive. I would have high S at the end, and I'd have low S at the beginning, right? So my S is increasing. Delta S is positive. Okay? So whenever we have a reaction involving gases, if my moles gas increases, I get a higher entropy, right? So that means delta S is positive. And if I have a decrease in moles gas, that will be negative. You're going to do a homework problem where you're going to have to figure out delta N. This is the number of moles of gas. So we are only looking at the number of moles gas, not the total number of moles. All right. So that's it for entropy, predicting this sign. Let's do a few other things with entropy. And these are, look at what we call the laws of thermodynamics. Now, we already did the first law of thermodynamics. That was that total energy of a system is constant. The second law of thermodynamics says that changes that increase the entropy of the universe are spontaneous. What that means is we have this term delta S universe. Okay? Delta S universe is the delta S of my system, whatever reaction, and then the surroundings. So if a reaction causes this delta S of the universe to increase, that means the reaction is going to be spontaneous, right? So delta S universe is positive, greater than 0, spontaneous, less than 0, non-spontaneous. If it's exactly at 0, this is what we call a reversible reaction. Okay? Now, what this law really means is that the universe likes disorder. Okay? I have here a bunch of pens. I have them all nicely lined up. I'm going to drop them on the floor, right, or on the table. Now, you can't see it, but you know it's not going to fall in one piece, right? It's going to actually come up, and it's going to make something that is more disorganized. And I'm taking a picture of it so you can say, hey, it is more disorganized. Same thing if I had a deck of cards. If you ever heard that joke, 52 card pickup, right? You want to play a game, 52 card pickup, and then someone throws the cards on the floor and says, pick them up, right? The universe likes disorder. We're not going to spontaneously have something get more organized. In the same way, that room we had at the beginning, it over time becomes more disorganized because that's the universe. Over time, it doesn't somehow get more organized. All right, so our third law of thermodynamics is that a crystalline solid, so if we have a solid in a crystal, kind of like an ionic solid or salt, at 0K, the entropy is 0. Okay? It will have no vibrations or anything. It'll be perfectly still. This is because of that one definition we had of S, where it's equals K times ln of 1. So if it has no vibrations or anything, S is equal to 0. By the way, have we ever gotten to 0 Kelvin? No. The lowest it's ever gotten is 500 nanokelvin. That's let's see, 0, 0, 0, 0, 0, 0, 5 Kelvin. That's really cold, but not quite 0. In fact, it may not even be possible to get to exactly 0 Kelvin because that may be physically impossible. All right, so what does this mean? Okay. Well, because of this, we can use 0 Kelvin as a baseline. Every compound at 0 Kelvin will have an entropy of 0. So we can basically say, hey, anything from that, right, my S1 or my S initial will be 0. So instead of having delta S, I can just say S. So I can have standard state entropy of a substance. This is the entropy at temperature equals 298 K in relation to at 0 K. Well, that's just going to be S because at 0 K, it's 0. All right, so these are in joules per mole K. You can see these entropies or these standard entropies. They're all in the back of the book. Appendix G, the same place we got our heats of formation. And we can see all of them based on that first element. Notice here that water vapor, H2O gas, has a higher entropy than H2O liquid. That makes sense because liquid water isn't as disorganized as gaseous water. Okay, so what does this mean? Well, because remember that second part of Hess's law where we said we can find delta H based on delta HFs? Well, the same thing is true for entropy. We can find delta S for any reaction, the change in disorder, based on the standard entropies, right? So we have the same equation, products minus reactants, sum them all up using the stoichiometric coefficients, except instead of delta S, it's now just S naught or standard entropy. All right, so let's use this to figure out delta S for this reaction, okay? So I have SO2 gas plus 2OH gas going to form H2SO4 liquid. I'm going to go ahead and I'm going to get those standard S's, but before we even do that, we can look at this and we can say, should this delta S be positive or negative? So what we're going to do is we're going to look at our reactants and our products, and we're going to see which one is more disorganized. Okay, now, because there are gases involved, all I care about are the gases, right? Why? Because over here, I have SO2, which is a gas, and I have 2OH, which are also gas. These are all whizzing around, bumping the walls, causing pressure, all that stuff. And over on this side, all I have is some liquid at the bottom, right? That liquid may slosh around a little, but it's not as disorganized as over here, okay? So I could go ahead and I could say, here, I have 3 moles of gas, whereas over here, I have 0 moles of gas. So in this case, my delta N is negative. I'm losing moles. So that means my delta S is also going to be negative. Okay? All right, let's go ahead and just put this another way. This is high S. This is low S, right? This is more disorganized. So my delta S is going to be high or low minus high. That's going to give me a negative value. Okay? So I already know this should be negative. Let's actually go ahead and use our standard entropies in order to figure this out. All right. So if I look at the back of the book in the appendix, I can find S naughts for all of these. For SO2, it's 248.2 joules per Kelvin. Okay, mole Kelvin. All right, for OH, it's 183.7 joules per mole Kelvin. And for H2SO4, it's 100.0 joules per mole Kelvin. These are all from the back of the book, Appendix G. And so I can just say that delta S is going to be products minus reactants. So I do 100 times 100 joules per mole, okay, minus 248.2 times 1 plus 2 times 183.7. Okay, I have this 2 here because of this coefficient. All the other ones are 1, so I don't include them. All right, so this gives me 100 joules per mole K minus let's see, this will be, I haven't done this, so let me just do this real quick. 248.2 plus 2 times 183.7, that's 615.6 joules per K. Oh, by the way, seeing that I'm multiplying by moles, this moles goes away. So this is going to get me negative 515.6 joules per Kelvin. So this means that my entropy decreases. And I knew it was already negative because of that. Let's go over this one more time on the screen. So we start off by finding our delta G's from the back of the book. Then we plug them into our equation up here, and we get our answer. And our answer goes and it agrees with what we thought it would be at the very beginning. All right, so this equation is very much like the one we had for Hess's law, right? So go ahead and do video problem 3B. This is using these standard entropies from the back of the book, right? Use these to figure out delta S for these two equations. Okay. All right, so that is it for entropy. Entropy is the number of microstates, or better, the amount of disorder in the system. So if delta S is increasing, that means that it's becoming more disorganized, right? Our houses, as we're living in them and just like throwing stuff everywhere, our delta S is increasing, okay? All right, and then we have these 3 laws of thermodynamics. We already talked about the first one before. The second that says that the universe likes disorder. And the third says that at 0 Kelvin, S is 0. So we can use this equation right here to figure out delta S for a reaction. All right, so that's it for lesson 5. It's a little bit shorter because next time we're going to pull together all of the thermodynamics, enthalpy, entropy, and we're going to come up with one other term to talk all about things that are spontaneous. All right, see you guys next time. Bye.